Okay. Um, Today we're going to continue what we started last week, which is Monte Carlo method for reinforcement learning. And specifically, we'll focus on off-policy methods. The audio is very low. Is it better now? Okay. All right. So specifically, we will focus on off-policy learning methods. But before that, let me recap what we have seen. So Monte Carlo methods are our first approach to real reinforcement learning problems. And guys, I can't change more than this the audio. Now, I think it's the same. How about now? Is it better now? Hello? This way? Hello? Hello? Is it better now? No, I will never put the microphone inside the mask. It's against any rule of, for health protection in the... guys, I'm having it in my hands. Anyway, let's continue. Probably you need to use some headset at home, otherwise you will never get any good audio. This is the best I can do, keeping it in front of my mouth with my hands. Okay, so we're going to talk about, let me put in presentation mode. View, full screen mode. I will try to put it. Okay. Okay, so we have seen Monte Carlo methods that are the first approach in our lessons to more realistic reinforcement learning problems. So this is the first scenario where you have multiple states and an agent that takes actions, and it has to estimate a complex value function. And it does that by using returns. Sorry, guys. We have been instructed to ask you to spread more than usual. Okay. It uses full returns, where we have said, just to repeat it once more, returns are the sum or discounted sum of the rewards from that state by following a certain policy. Okay. So by estimating this expected return, the agent computes a value function, and this value function is used then to compute a policy. We have seen specifically that we're not going to use the V value function, the state value function, because that requires a one-step look ahead, right? I need to take an action to see what is the value of the next state. So we cannot really do that. because we don't have a model, so we use a Q function where we estimate an action value function, which is the expectation of the return I would get from a certain state by taking a certain action and then following a certain policy. Okay? So we have seen specifically two approaches for Monte Carlo um, methods for estimating the value function. So the first visit and the every visit approaches. We have seen that basically they just differ by the fact that um, you don't really use every return that you get for the same state in the case of the first visit, but only the first time you visit that state, as the name suggests. We have also said this is good, and it's probably the most studied case, but for function approximators like neural networks, you probably will use something like every visit approach. So we have seen then how we can compute, we have seen some examples, and we have seen then how you can compute a policy out of the value function, and we have said that if we are greedy, with respect to this value function, we can basically improve our policy step by step, because it's sort of a moving target where we estimate the value of a certain policy and then we improve based on that, and we then recompute the value, and so on and so forth. So this is quite similar to the policy iteration algorithm, except that while we had the model in the policy iteration algorithm, here we are estimating everything and we don't have a model, so we don't use the transition probabilities. So we have seen the policy improvement theorem, which is basically what I just said. And we also said in order to be able to improve our estimates and to improve our policy, we need to also explore, because otherwise we are stuck in the same estimations, both of the value function and the policy. So in order to do that, we have said we could do something like exploring starts, where with a certain probability we select every state and action pair to start our episode. We have also said that this is quite unrealistic. You cannot do it every time, so we switch from that to something for the on policy case, right? To something which is exploration based on epsilon greedy, and this is where we stopped last time. So exploration based on epsilon greedy policy means that the policy that we use only during learning, at learning time we have a policy that is greedy 1 minus epsilon, with a 1 minus epsilon probability, where epsilon is a very small value. You determine the number. It can be typically set between 0.1 and 0.0001, something like that. So you need to tune that parameter. And otherwise, with probability epsilon, we select a random action. A policy that is assigning a probability which is greater than 0 to every action is called a soft policy. So in this case, when we consider an epsilon greedy policy, we are dealing with an epsilon soft policy, okay, where the probability of every other action except the best one is epsilon divided by the number of all the actions. So this is the on policy case. So what does it mean to be on policy? Being on policy means that we are estimating the value for the same policy that is generating our transitions. What does it mean practically? It means that I start with for example, with a random policy. I execute this random policy. I collect data from this policy, and then I estimate the value of this policy, and I improve that same policy. So at the next time I execute the policy will be different, okay? And it will be the same policy that generates the data that we're using for learning. Okay. So here we have seen the pseudocode of the on-policy Monte Carlo control with the epsilon greedy learning. epsilon greedy policies. Now, what does it mean instead to be off policy? So in the off policy case, the situation is slightly different. So in the off policy case, we have two different policies. One is the target policy, and the other one is the behavior policy. So the target policy is the policy that we are learning about something. I mean, we are trying to estimate something about the target policy, or we are trying to learn the target policy. The behavior policy is the policy that generates data. This means that we have two separate policies. One is the policy that I'm executing, which can be hand-coded, can be whatever you want, but it's a different policy from the one that I'm trying to learn about. Okay? And then the other one is the usual one, the one that we are trying to learn, and the one that we are trying to estimate the value for. Okay. So how does this work, and what are the assumptions that we need in order to have this working? So what we're trying to do, as I already said, is we're trying to estimate the V pi or the Q pi for the target policy pi. So we're calling the target policy pi. And we said we are generating data, so we are executing the policy B, which is the behavior policy, which is the one that is running our episodes. In order to do this, we need some assumptions that need to be respected. Specifically, the most important ones are the fact that every action that is taken under the policy pi, so every action that has a probability in pi of being selected greater than 0, has to be a probability greater than 0 also for the behavior policy. What does it mean practically? It means that if an action is selected or is going to be selected by pi, we also want it to be selected with some probability by the behavior policy. This is called the coverage assumption. So this implies that B has to be stochastic in the states where it is not identical to pi. And this is, of course, done because you need to learn something about the actions that are important to pi. And in order to do that, you need to collect some data. So B needs to ensure that you visit this information, you collect this kind of information that is relevant for pi. This also implies that the target policy is typically deterministic and greedy with respect to the current estimate. So you don't need to be epsilon greedy, right? Because we said last time, in the on policy case, we need to be epsilon greedy only during learning. So the target policy in this case is just exploiting the information that it's learning. And we don't need to explore by using the target policy. We explore by following the behavior policy in this case. So the behavior policy is stochastic in this case, so it can be epsilon greedy, for example. So one way to basically assign some information collected by B to pi is by using importance sampling. So this is basically telling us how important is the information that B has collected to pi. Okay, so and this is done because of course you are trying to compute some estimates in expectation from values that are collected under a different distribution. So you need to sort of balance this information based on the target distribution of data. So you are doing this by weighting the returns. So you compute some weights. And these weights, you will see that are nothing else than a ratio of probabilities. And these are called specifically importance sampling ratio. So again, these are tending to the target policy, how important is for the target policy this a certain data. So how you collect, how do you get to this kind of information? What is the derivation of these important sampling ratios? Simply, if you look at what a trajectory is, you can see that the probability of a certain trajectory, um, where the trajectory is sampled from the policy, is the product, of course, of the probability multiplied by the transition, the probability of selecting a certain action, multiplied by the probability of a certain transition, and so on and so forth, right? This is if you know uh, the model, right? So this becomes something like this. Now, if we want to compute the relative probability, right, which is the ratio of this um, of how the trajectory would have been sampled by the target policy compared to how the trajectory is sampled instead by the behavior policy, you simply can get rid of because you simplify this and this get deleted. So you can get rid of the transition um, information, so of the transition probability, which leaves you with just the division of pi and b. So this is basically how you are computing your importance sampling ratio, which is your weight for a certain return. So basically what you do in the end is you multiply, you compute in your expectations the value function just as the multiplication of these importance sampling ratios and the return itself. Nothing very difficult in this case. Um, there is ordinary and weighted importance sampling. I mean, you don't need to necessarily focus too much on this difference. The important thing that you need to know is that for off-policy learning, you typically use uh, importance sampling ratios that are some weights that you compute as the ratio of the probabilities that are of selecting a certain action that are generated by the two policies, the target policy and the behavior policy. Um, yes, okay, so here there is some example. If you recall the blackjack situation, we formulated the blackjack problem in the form of a macro decision process where we basically ran I mean, we didn't run it, but we simulated the run of our algorithms, and we have seen some plots out of them. So if we consider an every visit method for both the ordinary and weighted importance sampling ratios, and we'll see the pseudocode in any way, in any case to do this, you'll see that you get some mean square error, which is lower in the case of weighted importance sampling compared to the ordinary importance sampling ratio. This is just because typically you have um, in the case of the weighted importance sampling ratios, you typically are more unbiased, but your variance is typically smaller in the case of weighted importance sampling ratios. This is some other example. And we have said that in order to compute these importance sampling ratios, we compute these weights and we use the full trajectory, right? This is the way we have formulated the problem here. We said we need to use all the steps, the full trajectory, right? All the actions and all the states that are selected in the full trajectory from a certain state until the end, like we do for the returns, right? We sum everything from a certain state, all the rewards from a certain state until the end of the episode. But for computing the returns, we have also seen that there is another way, which is an incremental way. Similarly, there is an incremental way to compute these important sampling ratios. And this is um, expressed here. So how we are updating now our V function. We're updating our V function by the usual formula, right? So this is old estimate plus some alpha that multiplies our target minus our current prediction. Our current prediction is again B. Our target is the return. And here we select our alpha as the weight divided by C of n, where C of n is estimated similarly in incremental way, just as the sum, incremental sum of the weights. Okay? So the final pseudocode for this off-policy Monte Carlo prediction is the following. You start, as usual, with a value function for Q, which is initialized as you want, and then you loop until convergence by following a certain behavior policy, as we said, where the coverage assumption is respected. By following this policy, we generate an episode, we generate a trajectory, and then we initialize our returns to 0 and our weights to 1, and then we loop until the end of the episode. We estimate incrementally, as we did already see last times, the return as the discounted sum of the next return plus the current reward. Note that here we are moving backward. This is why we are able to do this, right? We are using our most recent, so the latest estimates for the return, and we are going backward so we can discount just the return and sum the older reward. Similarly, we update C by using this W. We update our Q by using this formula. And finally, we update our W by multiplying our previous weight by this ratio of pi and b for the selected action given the state, for the action, and yeah, for the selected action given the state, and for both pi and b. Okay, so what are the pros and cons of these of policy methods? So the good thing is that the behavior and target policy may be unrelated, and um, this is not written in the slides, but specifically one very interesting thing of policy learning methods is that you can, by following a single policy, the behavior policy, you could simultaneously learn something about 10 other different policies, right? Because why? Because I don't need to execute them. I'm just using collection of data from B, from the behavior policy, and then I'm updating by using, for example, important sampling. Um, I'm updating my target policy. So I can have 10 different target policies. I'm updating all of them in the, so in this loop here, I would basically execute uh, this step here and this step here for each policy that I have, right? And of course, I need to change W as well. So the return would be the same because this is coming from the trajectory. Then I would have for each policy, so another loop here, for each policy that I have, I would use its estimate of C, its estimate of Q, its estimate of W, and I would update each of them individually. So this is very powerful in theory. In practice, I mean, It's not so successful because learning is low, and sometimes the target policy may be a bit, as I mentioned, too unrelated. So it's good that it can be unrelated, but it can be too much unrelated, which means that you don't get enough information for certain states and actions that are relevant for one of the target policies. Um, so, yeah, okay. Okay, so here there is the final piece where we also add the control part, so the computation of the policy, how we update our policy, which is the usual thing. We just do an argmax over the Q function. Okay, so before moving forward to the next topic, I want to see if there are questions, and I will show also some code on Colab that I have uploaded already. Okay, so guys, for this I can't do a lot, right? Because I've been taking the time to have you asking questions. So this is, instead of losing time telling me that this is too fast, ask questions where you didn't understand, so we can go back and cover the topic. Huh? So this is a useless comment while you could ask questions instead. Okay, for first visit Monte Carlo method, estimate V as an average of returns following the first visit to S, but if the first visit isn't the return just one, I don't understand your comment. If the first visit isn't the return just one, so no, the return for the first visit it will be the sum of the rewards that come after the first visit to that state. So it's the discounted sum of the rewards that come after a certain state. So if you have a trajectory, let's say you visit state, let's say you have three states, A, B, and C, and then you have a trajectory that is generated by your policy, which is A, B, 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 C, B, A, B, 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 then only the second state is the first visit to B, right? And then from there, you will sum all the rewards until the end of your trajectory. Huh? Okay. Okay, so this is a more specific question. We can get back to that formula. So the product in the first slides for the off policy, where we compute the returns. Sorry, where we compute the important sampling ratios. So I don't know if you're referring to this or to this. I think you're referring to this one. And let's go back to this slide that is helping us to understand how we get that. So we said, if you have a starting state ST, then the probability of a certain trajectory under the policy pi, and this is nothing new because this is something we have seen already from our probabilistic reasoning part, right? The probability of a trajectory will be the product of the transitions, right? Transition probabilities. And so the product of being in a certain state after sampling a certain state and other action, so right, the probability of transitioning in a new state, multiplied by the probability of selecting that action. Right, so if we have the probability of selecting a certain action, we can compute the probability then of transitioning in a new state because we have the transition probability, if you have the transition probability. So this is, if you have the transition probability, this is how you will compute the probability of a trajectory. So it's just the product for starting from state t, right, t, until the end of the trajectory. It's just the product of the policy and the transition probability. So this is straightforward. Now, I said I use important sampling ratios as the relative probability, right, of the trajectory that is generated by B, which is the behavior policy, and the trajectory, the same trajectory, how it would have been generated by pi. So with which probability this would have been generated by pi. So this is to recap, this is the probability of a trajectory that is generated by B, and this is the probability of the same trajectory as it would have been generated by pi, as it would have been generated by the target policy. Just again to repeat, the trajectory is generated by B. So this is the probability of the trajectory that is generated by B, while this is the probability of the trajectory as if it was generated by pi, even if it is not. So why do we want to do this kind of ratio? We do this kind of ratio because, yes, but please ask questions on slide or not on chat. So why do you want to do that? Because you want to understand the importance, right? The importance of some data that are generated by B for the target policy. So if so let's say that policy pi would have generated a certain transition with a very small probability, right? So while B would generate that transition with very high probability, this weight is going to be very small, right? This is big. Why? Because this is small, this is big, so this is very small. So this means that this data for the target policy is not relevant in the end because this is some rare event for pi. While if this is very high, so if the probability of selecting a certain action in a certain state is high for pi and is very small for B, this means that this is a rare event that occurs when we execute our our behavior policy, which means we don't have a lot of data regarding this, which means that given we don't have a lot of data, we want to weight that a lot because it's a rare event, so it's important to keep that into account. Okay. Okay, so I hope this is clear now. Of course, the other thing is the probability of the trajectory here. For the probability of the trajectory in this ratio, we can get rid of the transition probabilities because this simplifies to one, so we don't need to use that for computing our important sampling ratios. And still, the important sampling ratios represent the probability of, the weight, the ratio between the trajectory probabilities for pi and for B. Now, an example of a behavior policy and a target policy. So let's say a behavior policy is, I don't know, for a robot moving in an environment, it will be, I will move forward with probability 0.9 and with probability 0.1 divided by 3, I will move either left or right or backward. So this is my behavior policy, which means the most of the times I'm moving forward. Then my target policy initially is probably random. And again, I'm learning about that. So it's not relevant what is the target policy at every single step. It's important what is at the end. But let's say that for for our target policy, at the moment, we have a very high probability of moving backward. And for example, let's write some numbers. Also here, the probability of moving backward is 0.9, and probability of moving either left or right or forward is 0.1 divided by 3. So we have the same numbers, except that this is for moving forward probability 0.9, and pi is for moving backward probability 0.9. So now what happens? If I get a transition where my robot is moving forward, right, this number will be very high. So this is 0.9, and this will be 0.1 divided by 3. Right, so this will be very small. And this weight, right, the importance that I need to give to this sample is very small, because this is not very relevant for the target policy. Vice versa, if I get a sample where the agent is moving backward, the robot is moving backward, this number is 0.9, this number is 0.1 divided by 3, which means that this is a big number. So I'm giving a lot of importance to this sample. Why? Because this is a more rare event, and I want to, and it's also very important for the behavior, for the target policy. So I want to keep that into account a lot. Then we said, if we compute our importance sampling ratios this way, how do we use them? We said we simply change the computation of the expected return by multiplying these importance sampling ratios by the return. So that's it. Let me see if there are more questions on this. Sort of, yeah. It's the relative, as I mentioned it. I already mentioned that it's the relative probability of the two trajectories. Again, keep in mind that you're dealing with a trajectory. So for a single weight, it's like the return. So the return is from a certain state until the end. The importance sampling ratio is the relative probability of the remaining part of the trajectory from a certain state between pi and b. So with the relative probability, we want to evaluate the samples generated by the behavior policy and by evaluating the expected value of what we want to know. Yeah, we want to compute the expected value of what we want to know by considering how relevant the data is for the target policy and how probable is for the behavior policy to generate that sort of trajectory, that kind of trajectory. Okay. This should be fine. Now, the difference between weighted and ordinary. So in ordinary importance sampling, you're doing a simple average. So you're dividing by the number t, where is the set of time steps where s is visited. So you're just averaging as you would do normally for the computation of the value function. So it's just an average where you divide your multiplication of the weight and the return by the number of times you're visiting a certain state. In the weighted case, instead, your division is on the weights themselves. So it's a weighted average in practice. Okay. Hope this is clear now. If you have more questions, I'm here. Any question in class? No. Is it because you didn't understand or because it's clear? Okay. Can you give some examples of behavior policy compared to pi? It's what I just did, right? I think I've given one clear example, even with numbers of. I mean, again, the behavior policy. I have given an example, right, with the zero 0.9 probability of the agent moving forward and zero 0.9 probability of target policy being moving backward, and yeah, I mean, I cannot repeat that, otherwise I'm really losing time, I think. So the example has been given. You can go back to the videos and uh, re-listen to that, I think. Um, the other thing that I want to repeat is that the only, I mean, there is not really a structure that needs to be there. So the only important thing is that um, the coverage assumption is respected, which means that if the probability of selecting a certain action in a certain state for the target policy is greater than zero, then this probability has to be greater than zero also for the behavior policy. There is no other constraint, really. So, um, for example, the behavior policy can be an epsilon greedy policy, while the target policy can be just a greedy policy. Okay? Um, Other questions? Okay, so guys, don't feel scared about asking questions when you have real questions. If you have just to say it's you went too fast, it's not useful. It's more useful if you ask what you didn't understand, because it will help your colleagues and it will help me in explaining what is unclear. So also consider that I don't have a lot of feedback here. I have two persons in the room, and when I was explaining, it seemed to be clear to them. So I was okay with moving forward. So consider the feedback is very reduced. So if you have questions, ask questions. Okay, so let's move on while eventually you ask questions to the Python notebook, where I have this has been uploaded already to Classroom, and um, I have here one example where you will see a non-policy Monte Carlo reinforcement learning algorithm being executed in a tabular way. I will also give you uh, some hints now on how to do this with a function approximator, so that you at least feel more prepared for when you have to do it yourself. Okay, so for this initial part, there is nothing new. I'm using the same Markov decision process that I have created last time, so I will not spend time on that, except saying that this is a grid word, and in this grid word, we want to visit some state. So we have our agent starting from this position, and this is our goal state. We have where we have some high reward for terminating in there. So here we have an obstacle. One represents an obstacle. Here represents a pit. So the pit is where the agent basically dies because it falls into the pit, and it gets a negative, very negative reward. And we have a step cost, which is a small negative reward that you get in every state, which is minus 0.4. Okay, so the terminal states, of course, are G and P, and the available actions for the agent are up, left, down, and right. So this is, again, the same MDP that I have used last time. Okay. Now, let me move on to the code here. It's a bit hard to do it with this. Okay. So here I'm initializing some structures in the form of dictionaries and so on and so forth, and just in order to keep easy for me to store the returns. So this is just a dictionary of that maps states and actions to the returns, and this is needed because, again, I need to compute the Q function, so I need to keep in mind what are the returns for a certain state by following a certain action and then following the policy. Here, I'm also defining a policy function, which is just computing the policy from a Q function. So simply, what I'm doing here is I'm averaging the returns, right, for every action and for every state. So this is the way I compute the Q, right? This is just an average of the return, and then of the returns, and otherwise I'm initializing this table randomly. And pi is computed as the argmax of the Q if the probability is greater than epsilon. Otherwise, with probability 1 minus epsilon, I'm doing this. And if otherwise, with probability epsilon, I'm selecting a random action. Okay, so this is my policy. So this is an epsilon greedy policy, right? So this is an epsilon greedy policy, and I'm computing my Qs as the average of the returns for every state and action, which is exactly what we have described in our code. So this preprocessed state is nothing very really relevant for the code. It's just something that is mapping the states in the form of a tuple, which is the index of the grid to a certain number that is the one that is relevant for me to map, just to map again the state to the action. Okay, sorry. And then for a certain number of episodes where I fix the maximum number of episodes, I reset my environment to initialize the environment. So to start from the initial state, I compute my policy. Okay, so that's the initial estimate of my policy. And then I use these visited state and actions in order to compute what are the ones that I have visited, to store them. And then I loop until the maximum length of an episode or the termination is reached, right? So when is that I stop my episode? I mentioned it last time. You either reach a termination state or you fix a maximum number of steps. So I look at my environment, I collect my state, I look at my policy, I collect my action, and then I append my state and action to my visited state and actions. I collect my transition from the environment, so I see what is the next state and next reward, next termination flag, and I append the transition to my episode. If there is a termination flag, I break. Then, after that, I'm looking backward in my episode, right? So I'm looking from the last transition that I got to the first one. I look at my state, I preprocess that. I also compute my return as in the way we already discussed, which is the iterative way. I use my last actually return multiplied by gamma, so I discount that and I sum the last reward. And this is the first visit method. So I'm doing if the state is and an action are not in the visited state and actions, then I append my return to the dictionary of the returns that is being used by the policy to compute by my utilities to compute Q and pi. So very easy. So if you look at the execution here, I'm doing a bunch of episodes. So episode 0, episode 1000, episode 2000. And you see that by the end of this learning process, the agent has been able to reach the goal state. So it started here, it moved right, moved up, uh, it moved up, but this didn't have an effect that we expected. So it moved up again, and moved right, and it reached the goal. So again, this is just to say how easy this is to implement in practice. It's just what is that I did, nothing really exceptional. I created a dictionary, so a table of Qs, a table of Pi's. The Q was computed just as the average of the return. A table of Pi was computed just as the argmax of the Q function with probability 1 minus epsilon, and otherwise with epsilon probability, I selected a random action. I just collect all my um, um, transitions, I compute the return, and then I update my table. Easy, very easy. Now, what changes? What is that changes if we are trying to do something in the function approximator land? So instead of using tables, right? So of course, the way I collect this information, so pi of state probably is slightly different. I will use the formalism of the framework. I'm using TensorFlow, for example. I will use the formalism for calling a function approximator in a certain state, which is pretty similar to this in any case. So it would be pi parentheses state and whatever. But the real thing that changes is here. So this is the training part, let's say, is the where I'm fitting my functions. The fitting here reduces to a simple average. But if I have a function approximator here, I might be, for example, just doing a similar thing. Let's say that this is my data set at this point, because this becomes my data set where I have my state and action mapped to a certain return. So my function approximator will take, for Q, will take the action and the state as an input, right? And it will be initialized randomly, because that's the way function approximators like neural networks are typically initialized. And then uh, I will use this data set to fit my Q function. So here I would be looping through my data set using a certain batch size. So for batch in my data set dot take, for example, if this is TensorFlow, then I have my data shuffled and I put as an input my state and action, and these are the returns. So those will be my labels. The returns will be my labels, and then I will use an L2 loss, like a mean square error, for example, to compute my loss. And then I will call the optimizer. The optimizer will perform the gradient descent on this function approximator. And again, however, pi will be computed the same way, in the sense that for pi, I will do argmax of Q if the reaction is random, or otherwise I will do, sorry, if the epsilon probability is if the probability is greater than 1 minus epsilon, otherwise a random action. How do I do it? The argmax in that case, I typically can either do pass as an input every possible action, or the other way to do this is instead of having both the state and an action being passed as input to my Q function approximator, I only pass the state, and my Q function approximator emits the Q value for every action. So this corresponds to something like this. Let me see if I can draw this. So the case that I have explained before is the following, where you have my neural network. This is my neural network. This is emitting the Q value. Sorry for the bad drawing, but I don't have my pen here. Q. And takes state and action as an input. Okay. Okay, this is A. Very bad A, but it's A. The other scenario is instead where you have, again, your Q as a neural network, but now you only pass as an input the state. And then you have different, so a number of outputs that corresponds to the number of actions. So in this case, we will have 4 outputs. So our neural network would be, for example, taking as input the state, and last layer of the neural network would have 4 outputs. 4 outputs corresponding to the Q of every action. Your question might be, but then how do I do the training for a specific action? You have a gating function here where you just basically, this corresponds to having a gator here. This is the gate. Where you basically put here the action that you selected, and this disables the gradient for every other action. So this is the action that I selected. So if this is A2, okay, let me write 2, it's easier. This will be enabling only this and disabling everything else. Okay. I can also try to upload an example of this in the next lessons, maybe. Let's see. But anyway, this is the idea. It's nothing more different, nothing different than this, or nothing more complex than this. Okay, so let's see if there are questions regarding this part. So that was the initial goal with the classes being done in offline and online way. So, but we don't have time to do that now. That's the problem. We don't have the material time to do everything. So I can upload the code, I can comment on that, but writing the code together, it's a lot of time. We don't have the time for this kind of exercitations anymore. Again, that was the initial idea. Now we can't. Other questions? You have questions? No. No. Okay. So if there are no more questions, we're moving then forward with the theory. And again, if there will be time, meaning that if we finish with the theory earlier, then I might be able to do what you asked. Otherwise, it's a bit hard to do some other something like this. Also, before I forget, let me say that tomorrow in theory we had the extra class. For this week, this is canceled, and we will find time in the upcoming weeks to do that because of the decisions that are being taken for the distance and all of that related to COVID. So until the situation is not clear, at least on the way teaching is going to be from tomorrow on, I would like to wait. So we'll either select another week of November or another week in December. And the other announcement is that during this week, I will upload the specifications for the um, optional homework. Remember that that would allow you to collect some extra points for the final exam. Except, of course, you cannot go above a certain number. There is still a threshold on the total outcome of your exam. Okay, I don't see more questions coming, so I will move forward. So this is the previous. Okay. So we have seen Monte Carlo. What is that we have seen so far related to Markov decision processes and specifically to reinforcement learning? So we have seen dynamic programming, which is more planning. It's not really reinforcement learning, and it makes use of a model. And we have seen Monte Carlo methods for reinforcement learning, both on policy and off policy. So what are the things here, the things to highlight? Monte Carlo methods learn directly from experience. They don't use a model. Temporal difference uses, temporal difference. This is an error. This is dynamic programming, DP. Um, estimates are based on other estimates. So on some previous estimate, we have seen the equations, the Bellman equations that are allowing us to compute um, an estimate based on another estimate, but using the model. So in temporal difference, we do something similar to dynamic programming in the sense that we use previous estimates, but without the model. And this is called bootstrapping. This process is called bootstrapping. So bootstrapping means that we are relying on previous estimates in order to compute our new estimate. So as usual, we'll first be focusing now on prediction, on evaluation part. So on the assumption that we have a policy, we see how we can evaluate the policy, and then we'll see how to do control, meaning how we compute a policy out of this process. So in Monte Carlo methods, we have seen that the central idea was the return. So we have seen the simple every visit method or the simple first visit method for non-stationary environments, and this was, and the update rule for the V function was the following: V gets, so new prediction, new estimate is computed as the previous estimate plus alpha that multiplies our target minus our previous estimate. The target for the Monte Carlo method was the return. And alpha, we said it was a constant step size. In temporal difference methods, our target changes, but this is still the target. So this part here is still our target. If you look at the overall formula, we have something like new estimate gets current estimate plus alpha, target minus current estimate. So the overall formula didn't change. We just replaced the target from being G in the Monte Carlo methods to this new other thing. We'll see now what this new other thing is, right? So this new other thing is nothing else than the sum of the last reward that we get plus gamma that multiplies V for the next state. So how is this different from the Monte Carlo case? In the Monte Carlo case, if we wanted to expand that, right, basically G, we had G here, so if we used the formulation in terms of rewards, this would have been plus gamma that multiplies G, right? So this would have been gamma that multiplies G. So we are replacing G with V now. But you also need to recall that V is nothing else than the expectation of the return. So we are just replacing the actual return with its estimate. Okay, so why is this useful? So this is useful because in order to update your value function, you don't need to wait the termination of the episode. You have one single transition, you update your value function at every transition that you receive. So in the Monte Carlo methods, we update our value function at every episode that we get. In our temporal difference methods, we update the value function at every transition that we get. And this is allowed by simply replacing this G with its estimate. Okay, so we are relying on an estimate to update our estimate, and this is called the bootstrapping process. So as I mentioned already, the update is based on a single transition from the old state to the new state, and the target, right, this is the overall target, the one that I have selected in red, is the reward plus gamma multiplying the value function at the next state. And this update is done every time a non-terminal state is visited. If you are in a terminal state, this becomes 0, so you don't have a next state. So this is basically to write the full formula. I will write it here. The exact formula is the following. Okay, so how is this different from, sorry, I'm missing the square bracket here somehow. I don't know why it doesn't allow me to write it. Anyway, there is a square bracket here that needs to be added. So How is this different from this formula? I'm just making explicit the fact that 1 minus termination has to be used, meaning that if the termination is true, this becomes 0. So all this part here is not considered. Hmm? Okay. Let's move on. Uh, okay. So as usual, we have our first pseudocode for a temporal difference method. Specifically for a tabular temporal difference method, we have the following. So for every episode, for every step in the episode, we update our v function by using the formula that we have seen uh, until the state is terminal. Now, you might be asking yourselves, why is this called temporal difference? It's called temporal difference just because a single transition from one step to another, so a single step of difference in time, allows us to update our value function. Instead, in the Monte Carlo approach, we had to rely on a full Monte Carlo sampling of a full trajectory. So yeah, bootstrapping means that the update is based on existing estimate. And this is basically what I already said. So the proof of the relation between the Monte Carlo approach and um, the temporal difference approach is nothing else than the fact that the value function is the expectation of the return given a certain state, which is the expectation of the reward that sums gamma multiplying the next return, which is, we can bring in this case the expectation inside, which is nothing else than the value function at the next state. So Monte Carlo estimate use the expected value of the, in Monte Carlo updates, we use the estimate because the expected value of the return is unknown. In dynamic programming, we use also the next value function, temporal difference. We do a similar thing, but without using the full model. So let's try to bring things together. So in temporal difference, in TD0, for example, we have seen that the update is based on one single transition that is sampled from the environment, right? So it's a sample. And Monte Carlo approaches sample a full trajectory. So both temporal difference and Monte Carlo methods use samples, and those are called sample updates. They are different update rules, but still they use sample updates. In dynamic programming, instead, we use the full distribution of all possible successors, which means that we are using expected updates. Okay, so when we introduced the this function here, this update rule, sorry, we said the general update rule, which I repeat again once more, it's new prediction becomes previous prediction plus alpha that multiplies the target minus the current prediction. This is the overall update rule. We say this is like an error, and we are moving in the direction that reduces this error. Right, similarly to what you would do with a gradient descent. Specifically, in the case of the temporal difference, this is called temporal difference error. So the TD error. The TD error measures the difference between the current estimate of the value of a certain state and a better estimate, where we're basically incorporating one new information, which is the reward, and this is instead the estimate for the next state. So why is this better? Because we are incorporating a certain information, right? We are incorporating some information that is grounded on reality, which is the reward that we are collecting in a certain time step. So the TD error at each time depends on the estimate, on the same state, and also on the estimate at the next state. And this is not available only until a certain transition is done. So now this is, just don't get scared by these formulas, so don't become crazy on this. This is just showing you that if the estimate of V doesn't change during one episode, basically doing Monte Carlo and temporal difference is the same thing. And this is quite obvious, even if you don't look at this formula. Why? Because we said here, we said that V is just the expectation of G. And if we don't update V for a full episode, it's like we're using G, right? In expectation, that's the same thing. And this is showing you the same thing. It's just showing you that if you expand this object over here just as the sum of all the TD errors, and you don't change V, it's just doing the same exact thing. Of course, if you're updating V, then this identity is not exact because you are doing something slightly different. But if the step size is small enough, then in approximation, this is still true. Okay. So let me show you one further one example here to understand further what it is happening. So let's say that these are a bunch of states. So we are leaving the office, reaching the car, exiting the highway. We are going on a secondary road, arriving in the home street and arriving home. These are our states. And we want to predict the total travel time by using one value function estimation. So our value function is the total travel time. Okay, we can do that. So we get information every time. We use that as the reward, the travel time for every single step, and then we compute the expected travel time. So in the Monte Carlo case, right, if this is a certain trajectory that we get, then, if this is the expectation that we have, then, and this is the actual outcome, so this is one single episode, the outcome of one single episode, we're waiting the full episode and we are bringing up everything, the value of every single state. So in Monte Carlo, if this is the actual outcome and this is our estimate, we're bringing up the estimate for every single state. In temporal difference, we're considering specifically how each step contributes to the final outcome. So, for example, in this case, we're bringing down the reaching car because it doesn't take a lot of time to reach the car, but maybe it takes more time to exit the highway. So with TDF, or with using temporal difference method, we're basically assigning immediately a higher value, or more quickly, basically a higher value or a lower value to the states that contribute the most to the final outcome. Huh? Now, let me pause it here before moving forward and ask and see if there are questions. Okay, so the homework, the details of how it works, I will write them on Classroom, so don't worry, they will be written on Classroom. You will ask questions if you don't understand something. It will be everything on Classroom, of course, not just on an announcement of this form. So the homework will be uploaded this week. So between today and Friday, you will find it online. Of course, you will get consistent time depending on how or when I upload that. Okay. Questions on the topic we were discussing instead, on temporal difference. Questions in class? So let me say one thing, which is maybe slightly different. So the feeling that I get from teaching this way is, in class, it seems like I'm going too slow, and at home it feels like I'm going too fast. So I'm also here, right? Okay. So good. At least it's not just my feeling. I'm sorry for you guys that are here. That anyway. Okay, there are no questions moving forward then. Okay. Okay, so what are the pros and also the cons of temporal difference methods? So by the fact that temporal difference learns a guess from a guess, the advantage over dynamic programming, over Monte Carlo methods, is that it's full incremental and online, so you don't need to wait the end of an episode. Also because episodes can be often very long, and learning can be slow. Some tasks do not have episodes at all, and also you need to consider the fact that by sampling full trajectories, you have a lot more stochasticity involved, which means that the variance is typically high for estimations that are done using Monte Carlo methods. Um, of course, this is more similar to dynamic programming, but we don't have the need of the model. So this is good because in the reinforcement learning we don't have the model. Otherwise, we would be doing planning. So temporal difference TD0 has been proved to converge asymptotically to the correct value function for a certain policy. In the case where the step size is sufficiently small, and probability 1 if the step size is decreasing. So there is no theory on the fact or whether the temporal difference or Monte Carlo methods learn faster or more efficiently. They just learn in different ways. In practice, you can see that temporal difference methods are at least faster for a constant step size on stochastic tasks. And again, you can imagine why, right? Because sampling trajectories often enough that are relevant is not said to be happening, while visiting states is easier, it's faster. Okay, so now we'll see one example where we look at the following Markov decision process without actions, meaning that this is a Markov reward process. So it's an MDP where you get rewards, but you don't have actions. Okay, so it's just a random walk. So you have a probability of ending up left or right with the same probability. So it's 0.1 left, sorry, 0.5 left, 0.5 right. And let's assume we are dealing with an undiscounted task. So the values from A to E are the following. For A, we have 1/6. For B, the true values. These are the true values that we have for these states are 1/6, 2/6, 3 over 6, 4 over 6, 5 over 6. Why? Because the only reward at 1, we get it if we reach this terminal state. Otherwise, we are always at 0. If we have a 0.5 probability of ending up left or right, starting from C, it's 1 over 2, right? So 3/6 becomes 1 over 2. So it's half probability of getting 1 and half probability of getting 0. And if you do the computation for every state, you will see that this matches this value function. Okay. Now, um, these are the true values, and oops, sorry. And these are the estimated value using temporal TD0. Okay, so we start with everything 0, and then I mean, by updating the value function, we quickly converge after 100 iterations to the true value estimates. Now, if we look at the root mean square error of the true value function and the estimated value function, you will see that Monte Carlo and temporal difference methods, when alpha is constant, they will eventually both converge to the true one. You see that the Monte Carlo is converging as well to the correct values. You see the error is very small, 0.05 at this point. But you also see that the TD error, root mean square error, is much smaller earlier, right, with a smaller number of episodes. So with less than 25 episodes, you are already at the root mean square error that you would get by using a Monte Carlo approach for 100 episodes. Okay, so how do we do incremental learning using temporal difference methods? So suppose you have a finite amount of experience, like for example 100 time steps. The usual approach is until convergence, you present your experience to the your function approximator or whatever you're using, and you change your value function by the sum of all the increments. Would you do one single update for the full experience that you have, and basically you do a batch update. So you take the full set of time steps and you parse all of them together, so in a batch. So if you do this kind of update, so with batch updates, TD0 will converge in a deterministic way to a single answer, independent of the step size, as long as the step size is sufficiently small. And yeah, the same will be true also for constant alpha methods. So if you look at batch training and compare over the same task that we were looking before, the prediction of the value of a certain state in the random walk case, with batch updates, you will see that still temporal difference methods behave, I mean, better, just in the sense that they learn quicker than Monte Carlo methods. Huh? So using batch updates is pretty common, and in practice is what I described before in the Monte Carlo case, right? I said you create some batch and you do your updates using these batches. There are a bunch of reasons for doing that, including the fact that the variance is typically reduced. Huh? So what is the optimal value estimate? There are two possible answers. One is the estimate that minimizes the mean square error on the training set, which is basically what Monte Carlo approaches are trying to do. So Monte Carlo approaches in practice are better on existing data. Right? So if you look at the trajectories that you visit, Monte Carlo methods typically perform better than temporal difference methods. While the other possible answer is the estimate that is correct for the maximum likelihood model of the Markov process. okay? So the maximum likelihood estimate is the one whose probability of generating the data is the greatest. And this is what temporal difference method do. So this also implies that if the process is Markov with temporal difference method, we are producing lower error on future data. So the temporal difference method behave better on future data. And this is also obvious on the fact that we have seen before. If you do the update, your update step by step, you're already expected to behave better in the future compared to Monte Carlo method that just rely on full trajectories. For this slide, we'll skip. You can just read it at home. It's not relevant for the purpose of this specific lesson. And it's just there for your curiosity if you want to look at that. Now we are introducing two of the most important algorithms that we are describing here. Two of the most important ones, not because they are the most used ones, but just because they are the ones that you need to know. If you studied reinforcement learning, you need to know these algorithms, otherwise it's like you don't know anything. Okay, so the first one is called SARSA, and the other one is called Q-learning. So SARSA is a non-policy method. Q-learning is an off-policy method. In both cases, we're trying to learn an action value function. So in both cases, we're trying to learn an action value function. And of course, we use this action value function to estimate a policy. As you can imagine, given that SARSA is a non-policy method, we need to be epsilon greedy in order to explore. So we need to estimate the value q pi of a certain policy. And we basically use the same TD error that we described before, except that this is odd Q. So the transitions become, instead of estimating the transition of the error between ST and ST plus 1, the TD error is computed using the transition from ST-AT to ST plus 1, AT plus 1, where AT and AT plus 1 are selected by the policy. This is a key thing to understand. These and these come from the policy, okay? So the update rule after every transition from a non-terminal state becomes Q of STA gets previous estimate plus alpha reward plus gamma of Q ST plus 1, AT plus 1 as we get it from the policy minus Q ST AT as we get AT from the policy. If a ST plus 1 is terminal, this is 0. We already said that. So I already said that. As on all non-policy method, the estimate of Q is for the target policy. So we are learning on the same. So basically, the behavior policy and the target policy are the same, right? If we want to generalize to having always two policies, in this case, the target policy and the behavior policy are the same in the on-policy case. Okay. And SARSA converges with probability 1 to pi star and q star, which are the optimal policy and the optimal q function, as long as all the couple of state and actions are visited an infinite amount of times. And pi converges to greedy policy. Again, here, in order to do this, we need to do exploration, which means that the policy needs to be epsilon greedy. So the SARSA pseudocode is the following. So we start from a certain state, we choose our actions by following an epsilon greedy policy derived from Q. And so we take our action, we observe the reward in the next state, we choose the next action from the policy, and we update our Q function according to the formula that we have seen before until the state is terminal. Q-learning is different because while Q, so we say that SARSA is trying to estimate Q pi, so the value of the policy. So it's specifically depends on the policy, and it converges to the optimal policy and the optimal Q eventually. Q learning behaves slightly different because it's trying to directly approximate Q star. It's trying to directly approximate the optimal value function, so independently of the policy. This is why Q learning is of policy. So in Q learning, the policy still determines in practice what are the state and action pairs that are visited and updated. And the update rule is the following. Q, so the new prediction becomes the old prediction plus alpha that multiplies the reward plus gamma that is multiplied by the maximum. So the maximum Q, right? The maximum Q, so you select the maximum Q over the actions, and on that you compute your error. Now you see why this is on policy, why this is off policy, because this is the maximum, this is using the maximum here, right? So this implies that we are trying to learn directly about our optimal policy. So our target policy is the optimal policy, and our behavior policy is still computed based on the Q that we are estimating, but in an epsilon greedy way. So our target policy is the optimal policy, our behavior policy is the epsilon greedy policy computed over Q. So the differences here between SARS and Q-learning are in the fact that SARS estimates the value of the policy, Q-learning estimates the value, the optimal value, which is implying that we are trying to estimate the target policy as the optimal policy. So why is it off policy? Because we're using the maximum here that implies this thing that I just said. So the pseudocode is basically the same as SARS, except that we are just replacing, we're not sampling the next action, and we are just doing this update rule here. So now, let's assume you have an environment like this. It's still a grid word, where you basically get a negative reward for every step that you take. You have a goal where you have a positive reward, and then you have a cliff where you are getting, and I will close with this example, where you're getting minus 100 reward. If you're doing SARSA, you probably will learn something like this, which is a safer path, because you're taking action selection into account. Because with SARSA, you're taking the action selection into account, meaning that if you, given that the environment is stochastic, if you fall in the cliff, you want to stay away from the cliff, okay? Q-learning instead just cares about the optimal action, so it will just go the short way, because that's the optimal thing to do in practice. And the fact that this is the safer path also depends on the fact that with SARSA, you're using an epsilon greedy policy. So if you're using an epsilon greedy policy, the action is random sometimes. So the action selection will lead to falling in the cliff itself. So Q-learning learns the values directly for the optimal policy. SARSA takes into account the action selection. And this is where we'll stop for today. There is a bit more details in the slide that I will discuss next time. And let me see if there are questions. It seems there are no questions. And if you have them, please ask them at the beginning of next class at this point. Okay. Thanks for your attention, and see you next week at this point. We're not having next